So, what's up, guys? So, I'm here to continue the lecture of virtual memory. Okay, so first is trashing. So, if a process does not have enough pages, the page fault rate is very high. So, that is one of the concept of trashing. Okay, so it says that the page fault rate is very high. So, first is let us recall what is a page fault. So, a page fault, when the demand page is not present or is not located in a main memory, so that is a page fault. Okay, so I will show you how page fault works. Okay, so uh, this load M, in this part, this is the CPU or the program. So the program wants to request the M or the reference M. So it will request or it will send the reference page to the page table here. So page table, it contains all the information from the physical memory. Okay, so it will check. So take note, the I here, whatever it is requesting, it is first invalid. Okay, so after in the page table, it the page table will send it to the operating system. So in this part, it will verify first if the reference page is invalid. If it is invalid, it is automatically aborted. But if it is just not on a memory, then the process will continue and the operating system will take charge now, and it will give the control to here. So this is the disk for page is on backing store. So this is the secondary memory or the disk, and the disk will find that page or that reference page, and it will bring now or it will send it to the physical memory. Okay, so this is a free frame from a physical memory, and it will bring the missing page and it will insert here in the free frame. Then the physical memory now will send it again back to the page table for resetting the page table. Okay, so if the demand page now is in here, back to the page table, the page table will send it back again to the CPU for restart instruction. Okay, so after restarting the instruction, so the CPU now again will send it to the page table, and let's just say that the reference M is now in this part with a valid with a V letter here. So it means that the M now is loaded on the physical memory. Okay, so that is how page fault works. So let's move back to the trashing. So this leads to low CPU utilization. Operating system thinking that it needs to increase the degree of multi-programming, another process added to the system. So that is the concept of trashing. And the definition of trashing is a process is busy swapping pages in and out. So it is a process, when the process is busy swapping pages to the memory, back to the physical, back to the secondary memory or the disk. So that is trashing. Okay. So next is the continuation of thrashing. So as you can see, the CPU utilization increases and the degree of multi-programming also uh, moving to the right. So as you can see the graph here, at this part, the CPU utilization is being increased while the multi degree of programming are busy. So at this part, this is the thrashing part because uh, it is now busy swapping and swapping input and output of data. Okay. So next, the demand paging and thrashing. So demand paging and thrashing. Why does demand paging works? Or let us recall also first what is a demand page or demand paging. Okay. So demand paging could bring entire process into memory at load time or bring a page into memory only when it is needed. So less input output needed, no unnecessary input or output, less memory needed, faster response, more users. Page is needed, reference to it. Invalid reference is the result is to abort. Not in memory, then it will bring to memory. So I will show you uh, how demand paging works. So demand paging, this is the main memory, and this is the secondary memory or the disk. This is the disk. So at process 1, the program requested these references or the pages, and it is being used. So the disk will send uh, those pages or those references to the main memory. Okay, so this is the time swap in occurs. So the second process, so this process, the program is not using these informations or this data. So the memory will send it out to the disk because it is not being used. Okay, so that is how demand paging works. So swapping and basically swapping in and swapping out of the pages. Okay, so let's move back. About lazy swapper, never swaps a page into memory unless page will be needed. So you will only swap the page if the you will only swap a page here like in here if uh, the pages are being needed in the memory. But if it is not needed, so the memory will send it back to the disk. Okay, so that is how demand paging works. So why does demand paging works? Locality model process migrates from one locality to another. Localities may overlap. So why does thrashing occur? Size of the locality is greater than total memory size. Limit effect by using local or priority page replacement. So that is demanded paging and thrashing. So page fault frequency. Establish acceptable page fault frequency rate and use local replacement policy. If actual rate is too low, process loses frames. If actual rate is too high, process gains frame. So basically in this graph, so the going up arrow is the page fault rate and the arrow moving to the left, right is the number of frames. Okay, so if the page fault is high in here, so the demand of frames is increases. So it increases the need of frames. But when your page fault is in lower rate, So the demand of frames also decreases. Okay, so that is how page fault frequency works. So next, working sets and page fault rates. So in this graph, you can also compare this graph to when you open what do you call this, task manager. If you open the task manager, you can see a graph like this. Okay, so going up is the page fault rate, and moving to the right is the time. So at this part, this is your working set. Why? Because this is the time when you are using many programs here, the degree of multi-programming. So this is the busy time, and this part will occurs the so-called thrashing here. So this is the thrashing part. So the rate of your fault or the frames needed are being increased. So this is the time your CPU is being busy. Okay? So that is the logic of it. So next, so memory map files. Memory map file I/O allows file I/O to be treated as routine memory access by mapping a disk block to a page in memory. A file is initially read using demand paging. A page-sized portion of the file is read from the file system into a physical page. Subsequent reads writes to from the file are treated as ordinary memory access. Simplifies and speed file access by driving file input and output through memory rather than read and write system calls. Also allows several processes to map the same file, allowing the page in memory to be shared. So uh, I will show you a graph later on how memory map file works. So some operating systems uses memory map file for standard input and output. Process can explicitly request memory mapping a file via memory map system call. Now file map into process address space. For standard input output, open, read, write, close, memory map anyways. But map file into kernel address space. Process still does read and write. Copies data to and from kernel space and user space. Uses efficient memory management subsystem. Avoids needing separate subsystem. Memory map files can be used for shared memory, although again via separate system calls. So now this is how memory map files works. So this is a process. This is a program. So process A, virtual memory. Process B, virtual memory. So this is your disk and the physical memory. So now your disk gives the pages into the physical memory or your RAM. Okay? So now the two process uses the same pages on the memory. So basically the concept here is in the next graph here, this is a general graph of how memory map file works. So a process 1 and a process B. So the shared memory here are being used also by process B by one shared memory. So this is the one shared memory, and it is being used by two processes at the same time. So that is how shared memory works. So that's end my lecture on virtual memory. Thank you and God bless.